I almost made it on that last one. So this is a very, very important tool to have around, this remainder theorem on number 5. And again, if I ask you to use the remainder theorem, you got to show me the synthetic division, and you have to state your answer. Here the answer would be P of 1 equals 6. P of negative 2 equals 0. Don't just do the synthetic division. I want you to make sure you tell me, well, what does that mean? If you do the synthetic division, show me 6. Make sure you show me that that means you know P of 1 is equal to 6. If you want to plug that 1 in and check, go for it, check. But make sure I see this. Use the technique, or I can't give you points for it. Okay, that's number 5. Number 6, you're given a polynomial. I believe it's the same polynomial. 2x to the 4th plus 3x to the 3rd plus 3x minus 2. And you're asked to make a list of all possible rational zeros. Now, this is also one of those questions that a lot of people tend to make more difficult than it has to be. This is not asking you to solve this question. It's not asking you to graph it, factor it, find its zeros, anything. It's asking you to make a list of possible rational zeros. That's our rational theorem test, or our rational root test. It's what we talked about at the beginning of that last video I put out for chapter 4 on the rational root theorem with the worksheet. If you haven't done that, do that. It's a nice example. But the rational root theorem, or rational zeros test, tells us that all rational zeros have to be of the form b over a, where b is factors of the constant and a are factors of the lead coefficient. The reason for this, really quick, as you might remember, all factors are going to be of the form ax plus, or I actually prefer minus b, where all the different ax's multiply together to make the 2x to the 4th, and all the constants multiply together to make the constant at the end. The other numbers in between are interactions of some of the b's and some of the a's, but every single one of those a's multiplied together should make that 2. So if they're rational, we should be able to take this and solve it, set it equal to 0, add over the b, divide the a, and if it's rational, it'll be of that form. So all possible rational zeros are every rational number that can multiply to make a 2. Well, that's a 1 and a 2. Can be positive or negative, though. Don't forget those. And every rational number that can make the lead coefficient, which also happens to be a 2, plus or minus 1, and plus or minus 2. So every single fraction that you can make out of those is possible as a rational zero for that polynomial. So 1 over 1, 1 over 2, 2 over 1, and 2 over 2. Of course, 2 over 2 is just 1, so no need to be redundant. Put in the plus or minus, and that is your list of possible zeros. You're done. You weren't asked to test them. You weren't asked to find them. You weren't asked to see which ones work, which ones don't. Don't do any of that if you're just asked to find the possible rational zeros. You can spend a lot of time doing much more than you have to. I think on the onlines you were asked to do this, you'd see like lists, and it would give you 3 or 4 lists, and you were asked to pick which one is the possible zeros. That's all this question is asking. Don't make it worse. Okay. Now, number 7. Oh, people love number 7. So, wait, where is it? There it is. We want to build a polynomial. Build a polynomial with some roots. With roots of x equals 2, 3, negative 1, where the degree, n for the degree, is 3. Or one could say of minimal degree. There's 3 numbers, so the minimum degree is 3. Such that, and here's always the hard part, such that f of 1 is equal to 2. So if we want to look at what we're being asked here, we are asked to make a polynomial, build a polynomial, that has roots of 2, 3, and negative 1. Now roots are the same thing as x-intercepts, or the same thing as zeros. So it should have an x-intercept, a 0, a root, at 2, 1, 2, at 3, 1, 2, 3, and at negative 1. So it should have zeros in those 3 spots. Now, how many different third-degree polynomials could we draw that go through those 3 spots? Well, we could draw lots of them. There's a third-degree polynomial that goes through those 3 zeros. There's a third-degree polynomial that goes through those 3 zeros. We could stay here all day and draw different ones. Hopefully you can see some of those. One more in green, a big one. So there's all kinds of different third-degree polynomials that we could draw that go through those 3 zeros. But only one of them is going to go through the point 1, 2. This is f of x equals function. So this is an x value and a y value. So at 1, 2, only one of these is going to go through the point 1, 2. And we have to figure out which one is that. Which one is that? Which one that is. The key here is for a polynomial to have these roots. If you have a root of 2, that means you have a factor of x minus 2. If you have a root of 3, that means you have a factor of x minus 3. If you have a root of negative 1, that means you have a factor x plus 1. Usually we're pretty good with that. The problem is we also might have a lead coefficient, a. Now if we're told that a, great. Sometimes the ones in the book would say, or the ones on your text would say, given that the lead coefficient is 2, great, make a equals 2. But we're not always going to be told that. So we don't know what number this is. And the difference between all of these different infinitely many third-degree polynomials that we could draw that go through those 3 zeros, they're all differentiated by what value that a is. Here the a is a little bit higher, here the a is a little bit lower. The ones that look upside down, that a is negative, this one a little more negative, that one a little less negative. So all of those differences have to do with what that a value is. And there's only one value for a that can make us go through that point. How do we find it? Well, we know, according to this, that if we plug in x equals 1, we're supposed to get a 2. So if we let x equal 1, 1 minus 2, 1 minus 3, 1 plus 1, times a, that should equal 2. Our job is just to figure out what a has to be to make this true. So 2 equals a times, what is it, negative 1 times negative 2 times 2. So 2 equals a times 4. So a equals, divide the 4 off, 1/2. So, whoops, yeah. So now we know what a has to be for this all to be true. So our polynomial is going to come from 1/2 times x minus 2 times x minus 3 times x plus 1. Now on your tests or whatnot, you should multiply all this together. I won't do it for sake of time right now. I do tend to tell people if this fraction, if it ends up being a fraction and it's kind of ugly, Multiply all this together, leave the fraction on the outside. It tends to be a little prettier, easier to work with. If this is a nice number, like 1/2's not that bad, particularly if there's a lot of even numbers in there. But if it's something like 17/29, don't multiply it through. Leave it out. If it's something nice like 2 or 5, -3, multiply that through. Clean it up. Use your own judgment there. But do multiply all this together. You also might review what to do if one of these is a complex number. That makes it kind of a good test question. If this was, say, -I, or this was 5 plus 3i, the process is basically the same, but you do have the complex conjugate issues, and multiplying it back together with complex numbers can be a little bit different. So that's a nice thing to practice. You can consider that a hint that may or may not end up on your test, but it is a good thing to practice. So, number 7, you have any questions about those? Let me know. But the big key is this A. You've got to remember that there's at least possible, that there's a constant multiple out here. And you're going to know that constant multiple based on knowing that if you plug in this value, the whole thing should equal that value. Okay, moving right along. Second page, number 8. So, number 8. Solve. Just solve. Good old solve. 2 to the 4th plus 3x to the 3rd plus 3x equals 2. Now, this problem on this test in chapter 4, when it just says solve, I think this one says solve the, it says solve the equation, but just solve, often throws people for much more of a loop than it has to. People can do all these first questions really well. They can use the remainder theorem. They know how to do the synthetic division. They know how to find rational zeros. People will often, oversolve this and actually factor this thing all out, like you did in that worksheet. So you'll show all those good, solid chapter 4 skills, and then you'll be asked, here, solve this, and people will stare at this and say they have no idea what to do. Well, this is a polynomial. When you had quadratics, when you were asked to solve quadratics, the first thing you tried to do is factor the quadratic. If you could factor it, you could pull out those solutions. This is no different. Just because it's a 4th degree polynomial, if we could factor it, we could pull out those solutions. All we have to do is be able to factor a 4th degree polynomial. Well, that's what all these other skills were for. That's why we talked about synthetic division. That's why we have that rational root theorem and the graph and all that stuff. So this is a great time to bring out those tools. We do want to find, the factored form set equal to 0. So it's really in our best interests to subtract that 2, get it set equal to 0. But now if you could factor this into 1, 2, 3, 4 pieces equals 0, each one of those pieces would give you a solution and you'd be done. So it's really important to have all these skills here for the possible rational zeros, for the synthetic division, all of that come to you as a methodology for solving and dealing with large polynomials. If you're asked to factor them, find their roots, or solve large polynomials, this is your tool. For those of you who are going on to calculus, this is where this starts to come up. We'll have a big polynomial that we'll have to find the roots for. And for classes, it's really common for me to say at that point, hey, break down this large polynomial, and they all kind of stare at me. And I have to remind them, remember rational root theorem, all that stuff. They go, oh, yeah. We got to make sure that you're connecting these tools as a method for breaking down and solving large polynomials. So your first step is generally to get that list of possibles. And the nice thing is this is the same polynomial that you've been working with on the sample the whole time through. Now that may or may not be true on your actual test, but just to simplify these things, I made it true on the sample. So that list of possible zeros is just that plus or minus 1, the plus or minus 1/2, and the plus or minus 2. So try those, see which ones work. There's only 6 of them, so really just trying all of them is not too bad. But you might look at your graph too. Graph it on your calculator, see what it looks like. I don't have my calculator with me, so I can't see what it looks like. So I'm just going to pick numbers. It's always nice to start with plus or minus 1. Oh, actually, we already do have one. As you recall, where is it? From number 5, it was that same polynomial, and we saw that negative 2 made a 0. So we know negative 2 works. Negative 2 is one of these. So let's go ahead and use the negative 2 on our polynomial. All 2, 3, don't forget the 0. 3, negative 2. We know that's a solution to this equaling 0 because that's what number 5 said. Again, don't expect them to all match on your exam. I tend not to do that because then if you forget the 0 in number 5 and you forget the 0 through the rest of the test, it'll mess you up. So I tend to use different ones on your exam. So be okay with that. But anyway, real quick, bring down the 2. Negative 2 times 2 is negative 4, negative 1, 2, 2, negative 4, negative 1, 2, 0. And good, that worked. We knew it worked. We did it before. But again, this breaks us from the 4th degree polynomial down to just a 3rd degree polynomial. So in that 3rd degree polynomial, again, we could pick any of these. See which one works. I'm going to pick, I don't know. How about 1? It's always fun when 1 works. Do we try 1? Yeah, we tried 1. 1 won't work. We did 1 over here. 1 gave us 6. So why would I try 1? That would be dumb. I'm going to try negative 1 again and see what happens. So what? 2, negative 2, so negative 3, 3, 5. It's not looking promising. Negative 5, negative 6. Okay. 1 and negative 1 didn't work. What about 2? You want to try 2? Try a nice big positive 2 there. 2, 4, positive 3, 6, 8, 16. That didn't work. Okay, so 2 doesn't work. I'm going to bring back down the 2, negative 1, 2, negative 1. I'll try a half. Again, if you have the graph, it can speed this process up quite a bit. But I think it's nice for you guys to see what happens if you don't. Though I only have 2 minutes to do that in, but that's okay. So bring down the 2. Half of 2 is 1. 0. Half of 0 is 0. Bring down the 2. Half of 2 is 1. 0. Hey, good. So we know that it factors into x plus 2 from this, and x minus 1/2 from that. And what's going to be left is 2x squared plus 2 from this. Again, 2x squared, 0x plus 2. Always ends with a constant. So 2 solutions we know, negative 2 and 1/2, the negative 2 and the 1/2. So heck, even down here we can start preparing ourselves for an answer, negative 2 and positive 1/2. But this also generates our other 2 solutions. Our fundamental theorem of algebra says 4th degree we should have 4 solutions, though some of them might be complex numbers. So this 2x squared plus 2, can we solve that? Well, sure. Divide out the 2. So x squared plus 1 equals 0. You could have subtracted the 2 out as well first if you want to. X squared equals negative 1. So x equals plus or minus the square root of negative 1. Or x is plus or minus I. So great. We've got negative 2, we've got 1/2, and we have plus or minus I. If you want to write that as I and negative I, feel free. So the important thing with this question, what I can't stress enough in the 30 seconds I have left for this video, is to make sure that those rational root theorem, all this synthetic division stuff, that all of these tools are occurring to you when you're asked to solve large polynomials. The worst thing that happens is somebody will have all of these skills in their repertoire, but when they're just asked to solve, it doesn't connect to these tools. Okay, so if you have trouble with those, let me know. Practice those. Next one.